Our eighth and final cycle, and our fourth geologic cycle, is volcanoes. And we're going to define a volcano as an opening in the Earth's crust which allows hot, molten rock, magma, ash, and gas to escape from below the surface. Now, if you've ever wondered the difference between magma and lava, magma is molten rock below the Earth's surface. Lava is molten rock at the Earth's surface. So as soon as that magma comes to the Earth's surface, it ceases to be magma and is now called lava. Now, remember, this whole topic, what did we say the first when I introduced this topic? Mr. Rogers' word of the day was interconnected. Just like earthquakes, volcanoes do not occur randomly. They are linked to plate boundaries. Now, remember, we can generate an earthquake at any of the three types of plate boundaries. We can generate it at a divergent, at a convergent, and at a transform. Volcanic activity is only linked to two of the three plate boundaries. We can generate them at a convergent boundary if we have a subduction zone, and we can generate them at a divergent plate boundary, but no volcanic activity at a transform plate boundary. The other location where we get volcanism is called a hotspot. And a hotspot is where a plume of magma rises to the Earth's surface from the mantle. I always think of Hawaii when I think of a hotspot. Hawaii sits on top of a hotspot, so does Iceland, and so does Yellowstone. If you've ever been to Yellowstone, the reason why you have those hot springs and geysers is because you have a plume of magma that rises close to the Earth's surface and heats the groundwater. Now, I want to show you, once again, correlation link between volcanism and plate boundaries. So here's our subduction zone. In this case, you have the Pacific plate diving underneath of parts of the Eurasian plate. And remember, as the plate dives in, the rock melts at a certain depth, that magma rises to the Earth's surface in the form of volcanism. Here's our divergent plate boundary in the middle of the Atlantic. This plate moves this way, this plate moves this way. Magma upwells. Once it reaches the Earth's surface, it's then lava, and we create new crustal material. And here's our hotspot. So you have this plume of magma that rises to the Earth's surface, creating the Hawaiian Islands. Now, once again, this is a picture of all the active volcanoes on Earth. An active volcano is a volcano that has erupted at least once over man's history. And so each of those red triangles represents an active volcano. You'll notice that if you trace around the Pacific tectonic plate and around the Philippine and the top of the Indian-Australian plate, this is where you see a lot of volcanoes. This is called the Ring of Fire, where 2/3 of all of Earth's active volcanoes resides, and it's all linked to those subduction zones. Remember, we have the Juan de Fuca plate subducting here, the Pacific plate subducting here, we have the Pacific plate subducting here, the Indian-Australian plate subducting here. So they're all tied to those subduction zones, those convergent plate boundaries. Now, we're going to talk about types of volcanoes. There's actually more than two, but I really just want to talk about the two main ones. And we're going to look at this as a spectrum. On one side of the spectrum, we have what are called stratovolcanoes. These are typically what you think of when you hear the word volcano. A steeply sided cone with a central vent at the top where material can be erupted out of. Now, these are the ones that when they erupt, they're going to be very, very explosive eruptions, very dangerous eruptions, but they're only going to erupt infrequently. So you might be talking about hundreds or thousands or even tens of thousand years between eruptions. The pressure has to build up again to create this explosive eruption. Now, if you take a look at a cross-sectional view of a stratovolcano, you see a very unique internal structure. So you'll have a layer of lava. Remember, lava is molten rock that's at the Earth's surface. And the next layer is what is called pyroclastic material. Pyro meaning fire, clast meaning bits or pieces. So pyroclastic material is anything ejected out of a stratovolcano during an eruption. And so you actually have a history of all this volcano's past eruptions. So lava, pyroclastic material, lava, pyroclastic material, lava, pyroclastic material. Now, whenever I think of stratovolcanoes, typically I always think of Mount St. Helens. Mount Rainier in the Cascades is also a stratovolcano. Mount Pinatubo in the Philippines, Mount Fuji on Japan, all of these are stratovolcanoes. Now, lucky for us, about 10 years ago, a fisherman that was passing by Papua New Guinea happened to catch a stratovolcano erupting.
Last week, this guy never stole this package off my porch. Because this doorbell camera doesn't just...
And so, right here, this is where the eruption is going to happen. See how those black pieces? That would be all that pyroclastic material.
The shock's coming.
That's the shock wave that hit.
Holy smoking Toledos. Man. That is something again.
So that's one side of our spectrum, our stratovolcanoes. The other side of the spectrum are shield volcanoes. These don't look like volcanoes. They're broad domes, they look like hills, with gently sloping sides that have gentle but continuous eruptions. Now, the main difference in intensity of eruptions has to do with the composition of the magma or lava. Our stratovolcanoes have what is called rhyolitic lava. It has high silica content, it has a lot of dissolved gases, and these tend to be the ones where the pressure builds up and builds up and builds up, and you get these explosive eruptions. Shield volcanoes, on the other hand, have something called basaltic lava. Basaltic lava has very, very low silica content, very, very low dissolved gases, and so this lava is going to be much more fluid. And so generally, shield volcanoes, what they do is they can shoot lava 10, 20 feet into the air, but no pyroclastic material, because you just don't get the pressure built up to those very, very high levels. Now, the best example of a shield volcano is Mauna Loa, which, by the way, is the largest shield volcano on Earth that's in the Hawaiian Islands. Now, what I have here is last year, 2019, Kilauea on the Hawaiian Islands erupted, and Kilauea is a shield volcano as well.
Shop our biggest online event of the year this Cyber Monday at livingspaces.com and get deals for every...
And so what you see here is you actually have multiple vents. The vent is where the lava comes to the surface, and then you can see the lava very fluid flowing away from these vent areas. There you go. Most shield volcanoes, you're just spewing lava 10 to 20, maybe 30 feet in the air, and then the fluid basaltic magma, or lava in this case, then flows away from these vents. Okay, so those are the two main types. Once again, you have the spectrum. One side are the explosive stratovolcanoes, the other side are the gentle shield volcanoes. Now, just like with earthquakes, we have things that we have to worry about, especially if we live near volcanically active areas. So let's talk about our volcanic hazards. And the first one are our lava flows. Now, generally this is what people think of the first, but lava flows don't cause really any deaths. You can outwalk a lava flow. However, they can cause a lot of property destruction because that lava can be anywhere between maybe 700 to 1200 degrees Celsius. And so they can cause homes, power lines to essentially go up in flames. We also have what is called a pyroclastic flow right here. This is a superheated cloud of ash and gas that can come traveling rapidly down the flank or the side of a volcano. When I say superheated, think 1000 to 1200 degrees Celsius. The pyroclastic flow is what killed everybody in Pompeii. If you've ever seen those pictures of those ashified mummies in Pompeii, what caused it was the pyroclastic flow from Mount Vesuvius. So Mount Vesuvius erupted, and this pyroclastic flow engulfed Pompeii and Herculaneum, two towns that were at the base of Mount Vesuvius. And so the nice thing for archaeologists is you can see what people were doing at the eruption because this pyroclastic flow struck very, very quickly. You might be talking about 100 to 200 miles per hour these things can move at. You also have to worry about pyroclastic material. Now that can be very, very fine material like ash. It also can be these what are called volcanic bombs, and that's anywhere from the size of like your hand all the way up to a Volkswagen VW Beetle. We also have lahars. Now think of a stratovolcano. Most stratovolcanoes, because of the high elevation at the top, they have snow and ice at their summit. So as the magma moves into the magma chamber, the heat from the magma melts this snow and ice, creating essentially a mud flow that once again travels down the side or flank of a volcano. So a lahar is simply a mud flow that occurs in volcanic terrain. Now we can also create a tsunami if we have an oceanic volcano. The 1883 Krakatoa eruption actually was large enough that created a massive tsunami that actually traveled thousands of miles away from where it was generated. We also have the deadly killers. What you can't see coming out of a volcano are invisible gases, sulfur dioxide, carbon monoxide, which can be very toxic or poisonous to biological organisms. Now here are your lava flows. Once again, not much to worry about in terms of loss of life, but as you can see, anything that's about 1000 degrees Celsius, once it touches a house, then the house goes up in flame. These bottom two pictures were taken from the Kilauea eruption last summer. You can actually see one destroying some utility lines over here. This one actually just touched this house, and now you can see the fires begin. Here are these pyroclastic flows. This was a very famous picture taken of the 1991 Mount Pinatubo eruption in the Philippines. This is the pyroclastic flow from the 1980 Mount St. Helens eruption. This picture was also taken somewhere in southern Asia during a massive volcanic eruption. All I can say is I am glad I am not that person right there. And then our pyroclastic or ejected material. This can be very, very fine material like ash that can be held aloft in the atmosphere for months, if not years afterwards, actually affecting climate. We'll actually talk about volcanism when we get to natural causes of climate change. Here would be a volcanic bomb. This actually just came out. You can see still very, very hot. And this is another favorite picture of mine. These boulders used to be up here. And in the geologic past, this volcano erupted, throwing these boulders miles away from their source, letting you know, very, very energetic, explosive eruption. And then lastly, our lahars. This is a pretty famous picture taken after the 1980 Mount St. Helens eruption. All of this brown that you see are these lahars that travel down the flanks of the volcano. Here's another picture of a mud flow. Now, in some cases, especially in Asian countries where there's a lot of volcanic activity, you might have villages that are near the base of the volcano. And in this picture here, you can actually see burying the houses. This mud flow actually came down a river channel, and you can see this mud flow actually originated from this volcano in the background. Now, this is the end of our Earth cycles discussion. I want to remind you, you now have your first exam, which will cover 3 topics. Introduction, the Earth systems. Remember, that was our introduction to chemistry, physics, and biology. And then today's Earth cycles, where we really looked at that 4th fundamental natural science of geology.